reactive-streams is a talk that we give in JavaOne in September 2016. So what I'd like to do over the next hour or so is discuss a couple of extended stream types that we've created in an open source library that we've released called Cyclops-react. So the structure of the talk is as follows. We're going to start with a section that explains the rationale behind the library, and then we'll develop as we go deeper into the library and the various extended stream types itself. So just kick off. So my name is John McLean. I'm the author of this library, the lead developer on that project, but I'm also an architect at AOL, and I work in our adtech division at AOL Platforms. In adtech, what we're trying to do is connect advertisers and publishers. So the old business model of an advertiser ringing up a publisher and asking to run an ad in his newspaper over the next week doesn't really work at internet scale. The old battle cry of the marketing manager, I'm wasting half my advertising budget, I just don't know which half, is a problem that we can solve on the internet because we have the data about who's looking at ads, who's clicking, and so on. We can help advertisers better meet their goals, and similarly we can use data to also help publisher meet their goals as well. So in terms of online advertising, interactions between advertisers and publishers are mediated by online exchanges. So as a user and you browse the web, viewing various different web pages, advertisers compete in real time in auctions to show you ads, and this is replicated across billions and billions of page views every day. So there's a real challenge of scale here. And typically in the ad tech industry, competing in these real-time bidding auctions to show users ads, ad tech companies need to respond on behalf of their advertisers within around about 100 milliseconds. For some exchanges, it's slightly less. For others, it's slightly more. And then if you think of that in terms of the requirements of the ad tech systems themselves, it means that internally each system must have a latency requirement of much, much less than that too. And so in AOL platforms, just in terms of display ads, we participate in around about 20 billion auctions a day, and that's growing rapidly. And what I mean by display ads is ads that we show on browsers, web browsers, as people browse the web on the desktop computer or laptop. And there is a similar number again across video and mobile. So typically I think we're talking tens of billions of requests every day, 60, 70 billion requests, participation in these auctions. As an engineer, this poses real challenges for us. All of the servers that we deploy our systems on today are multi-core. So Moore's law continues to hold, the number of transistors continues to double every couple of years, but the nature of Moore's law has fundamentally changed. No longer are we getting faster clock speeds with a single CPU, but we're getting extra processing power by adding extra cores, and that means that we have to develop concurrent applications, which we all know is easy, right? So as soon as you introduce concurrency into an application, you open up the possibility of race conditions, non-deterministic state, deadlocks, and so on. Within platforms, AOL platforms that is, I work in the forecasting division, or forecasting and optimization to be precise, but it's forecasting that I work on. We're not generating weather forecasts, but I guess some of the concepts may be similar. We're looking at past data and then trying to project out into the future how an ad campaign would behave to help our customers, the advertisers, better meet the goals for their advertising campaigns. The type of forecasts that we'll generate are something along the lines of this. For example, this is a price volume curve. And so what it shows is it gives an advertiser an idea that at any given bid price, how many ads they may expect to show per day. And typically we'll generate in the order of magnitude of 500,000 of these types of forecasts every day, and the responses need to come back in milliseconds. So the volume of data that we need to process to generate these forecasts is pretty large. We participate in, just in terms of display ads, in 20 billion auctions. Those generate 20 billion records. We display 2 billion ads, and then for each ad, just because we displayed it doesn't mean that it was actually viewable to the user. So we also generate a similar number of viewability records. Those are records that let us know whether a user actually saw the ad or not. So in order to generate our forecasts, we need to process all of this data in some way. And that means that we've got a challenge of scale. In order to do and generate our forecasts quickly, we have to process this data really, really quickly as well. And the raw log format is not really amenable to fast querying. So one of the core components of a forecasting system is an indexer, something that will take the raw data and convert it into a form that's more amenable for fast querying. So algorithmically at a high level, an indexer is pretty straightforward. You read data in from a log store. Once it's in memory, you convert it into a form more amenable for fast querying, and then once you've done that, you write your indexes out to a store. The challenge for us isn't the algorithm, it's the scale. And we know now that we're having to build these large-scale data processing applications on multi-core servers. Amdahl's law, which is pretty scary, lets us know the impact of sequential bottlenecks in our applications. So at a 95% parallel application, doubling the number of cores actually doesn't double our processing power. It gives us a marginal increase, a 5-10% increase instead. And that's pretty wasteful. So as engineers, that really poses the challenge for us to build applications that are not only highly concurrent, but very efficient in their concurrency as well. So whenever I sit down to write a highly concurrent application, I'm pretty optimistic. No matter how many times I've been burnt in the past, I always imagine that things will run very smoothly. The image of the puppies, I think it's well known at this stage, but I think it's very illustrative of the mental processes that I have when I write these types of applications, and I think that's fairly typical of engineers as well. No matter how many times things have gone wrong, we envision that we'll be successful this time. This time is different. Of course, when I actually sit down at my laptop and I code away, I've got my unit tests running, everything's passing, it looks great locally, and then I deploy it into an environment that has some data at scale, and kaboom, this is what happens. I've got bugs and I have got concurrency errors, and I'm tearing my hair out, and I've got to work late nights, high stress, to try and get things fixed. This isn't good, and it's not sustainable. But you work hard, you get things done, and eventually we have everything working in parallel and the bugs are sorted and everything looks good. Until we come in on Monday morning and our product manager says, well, we need new feature X or new feature Y. We're back into the code base and right back into the stressful fixing bugs and optimizing and finding difficult to find concurrency errors. So this was my life for a large number of years, building applications in a traditional imperative fashion in Java. And as we scaled up and in the amount of data that we had to process and the requirements we had for responsiveness, it became apparent that we were always going to be dealing with this challenge, and it was really, really painful. So that led us to think about better ways to build this type of software. So if this is a problem and you want to try and find a solution, I think a reasonable question to ask is, well, what's the root cause here? What's causing this problem? Why are things like this? So it's my contention that it's the introduction of mutable state that is the root cause of the complexity that we face in highly concurrent applications. As soon as you make a variable mutable and then you distribute that across threads, you've got the possibility of a reader trying to update the variable before or after a writer tries to read it. So you've got race conditions, and then to guard against race conditions you need to introduce synchronization or locking, which adds another layer of complexity, and you scale that up across large numbers of mutable variables protected by synchronization and locking, and you've got the potential for deadlocks now instead. So we layer complexity upon complexity, all because we introduced and then share mutable state. So this is what we were doing, building these types of applications in Java 7, using the low-level Java concurrency primitives to try and protect the mutable state that we had within our objects, as I think most typical Java development teams would have had. And then along came Java 8. So one of the nice things about Java 8 is that the new APIs it introduced were primarily immutable. The new datetime API, in contrast to the legacy date API in previous versions of Java, is immutable, and likewise with the cool new APIs that came in with completable future, optional, and stream, and so on. Another nice feature of the new APIs in Java 8 is their declarative nature. So no longer were we telling the computer exactly what to do, or how to do things. We were just saying what we'd like it to do and leaving it up to the API to implement it instead. And what this does is move a lot of the state from our application layer inside the APIs as well. And what we pass into the APIs, these lambda expressions, really should be stateless. And of course, we're really introducing concepts here from functional programming by the back door. And I guess if I told guys on my team, 3 or 4 months before the introduction of Java 8 that they'd be using monads and other concepts from category theory or Haskell, it would have freaked everybody out. But yet, that's what we're doing. In the stream API, we've got filter, flat map, map, reduce. These are all pretty advanced functional concepts, and I think it's fair to say that the guys that we worked with took to this like the proverbial duck to water, and that's probably true of Java developers in general. And it's not just in the stream API. Optional has them too. Flat map, map are there as well, and completable future has them as well. Even if it doesn't make them explicit, things like then apply is the equivalent of map, and then compose is the equivalent of flat map. But this cool new way of developing software doesn't come for free. There is a complexity overhead. This is a real example from our code base, and as you can see, it's pretty gnarly. So I was very, very happy to see this in our code base. And the primary reason for that is that the engineer that wrote this was one of the biggest opponents of introducing functional style idioms into our code base for the very reasonable assumption that it would introduce unnecessary complexity for an unknown benefit. Well, looking at the code, you can see he may have had a point there. But why I was happy about this was it showed that pretty quickly an engineer could get up to speed with managing this type of complexity. He could produce this code, he could understand it, he could manipulate it, even if it's pretty difficult to maintain. The next step beyond this is figuring out how to use it more sparingly and in a way that's much more maintainable as well. But he climbed the mountain, and he had managed to get his head around this way of programming very, very quickly. But it's absolutely true. There is a steeper overhead in programming this way than there is with simple imperative programming. The question is, are there benefits that outweigh this initial learning curve and complexity that developers have to get their head around? So one of the primary or principal benefits of programming in this way is that it encourages engineers to leverage pure functions. So if you're unfamiliar with what a pure function is, it's simply a function or a method that for any given input x always gives the same output y without impacting state outside of the function or method at all. So this type of function or method is inherently easier to test. There's no external state, there's less moving parts. You just pass in input x, and then you assert that input y comes out the other side. It's also inherently more optimizable because, again, for the same input x, you always get the same output y with no state changes elsewhere. So you can safely cache the result value. If you've called this function once, you know that x transforms to y. You can avoid the function call and just return y. But for the type of application that we're talking about here, one of the big benefits is the fact that in pure functions, there's no side effects. You don't impact state at all outside of the function. And that makes these types of functions inherently parallelizable. So here's an example of a pretty typical example of imperative Java 7 style code where we're populating a set inside a method in a list, and we're adding data into the set. Where we're adding the data into the set, that is a side effect. We're impacting state outside of the method. So this method, populate data, is impure. It's not a pure function. Conversely, we could rewrite populated data as a pure function, and internally within it we could leverage pure functions or lambda expressions using the stream API to do exactly the same thing. Key point here is that no state outside of the method is changed at all when the method's called. So we could write our unit tests for this method. We could write a pretty exhaustive test, and it's pretty straightforward because there's no external state. And then if we wanted to speed up this process of populating the set, we could parallelize this execution, and with the stream API, thanks to the parallel operator, that's pretty straightforward to do. So we can call parallel, and now we have parallel execution. And if we think of this in terms of our unit tests, the unit test we've written against the pure function version of this method will stand us in good stead once we call the parallel method. A question I would ask is that true if we had written this code in a typical imperative style? I leave that as an exercise for the listener, but I suspect that most people will agree that it's not. If you give this problem, how do you parallelize this imperative code to 10 Java engineers, you'll get 10 different solutions, all of which will probably involve some form of synchronization and locking, and your unit tests covering these will probably be a lot more complex than your equivalent code for the sequential version. So, to build highly concurrent applications, it's our view that the main source of the complexity or challenges is the introduction of mutable state, and the traditional imperative Java method of programming encourages engineers to introduce mutable state. One of the biggest impacts and benefits of Java 8 was not the API changes alone, but the psychological impact that those had on our engineers. Those new APIs that came in were primarily immutable and encouraged engineers to program in a fashion that was more stateless. But because they came in in the JDK from Oracle, it also kind of rubber stamped this alternative way of programming in Java. And prior to Java 8, where we had engineers who weren't overly keen in programming in this way, that post Java 8, the engineers took to it like ducks to water. And the biggest change here was really the fact that it came in the JDK, and this style of programming had some form of official rubber stamp. But for us, the APIs that were introduced were a big step forward, but probably not enough to really simplify the development of these highly concurrent applications. So for our application development, what we really wanted to do was discourage our engineers as much as possible to program in the old traditional imperative style, and encourage them more and as much as possible to adopt the new stream-like functional style of leveraging pure functions. And that's really the rationale and the driving force behind the library Cyclops-react that we've created. Our goal here is to encourage engineers to leverage this stream-like, more functional style of programming where possible, because it makes developing and testing and maintaining highly concurrent applications a lot more simpler. Okay, so if we want to encourage engineers to program more in this style, it would help if we had more powerful APIs that allowed them to solve more problems simply in this style. So a first port of call may be to offer extensions to the Stream API, and a good way to do that is by creating static methods that offer additional functionality that's not present. And that was exactly what we did. So let's talk through a couple of examples here. This is a real microservice that one of my colleagues is currently building. And what he'd like to do, it's a basic read, transform, write, but what he wants to do is read data in from S3. He wants to transform it in some way and then store it back into S3. Now the Stream API as it stands isn't particularly suited for this type of task, and we'll talk through why that's the case. One of the first things though that the engineer did once he had his stream set up and running was schedule it so it ran every 20 seconds. The Stream API itself doesn't support that, but we could write a static method that allowed you to schedule emission from a stream. And in fact, in Cyclops-react, we have a streamUtils class that has such a static method. It's called schedule, and schedule fixed delay. And so we can wrap our stream and pass it into schedule fixed delay along with how often we'd like to emit data from the stream, and then also a scheduled executor, so it executes asynchronously on a separate thread. In this case, emission of the next data point from the stream, where we go and we poll S3 and transform and then store back, happens every 20 seconds. And let's see an example of how that would run. So if we write a stream, in this case we're just going to iterate over integers infinitely and write them out to the console, but we've passed that stream into our schedule fixed delay method we're going to run this every 1 second. So once the last value's been printed out, we'll be triggered again 1 second after, and we're running on a scheduled thread pool. So when we run that, we see that every second the next integer is printed out as we emit one value from the stream on the schedule fixed delay every second. So the stream API itself isn't really suited to this particular use case, and there's a snag. A clue to the snag would be in what the method signature for the poll S3 method really should be. The stream API won't allow you to this because you can't pass methods or functions that throw checked exceptions into streams, and really this is there for good reason. Polling S3 is an I/O operation. It's calling into a remote service that may or may not be available, so it's inherently unstable. It could work, it may not work. You never quite know. But what happens if you call a method that throws an exception within a stream, particularly if you want to run this in a loop and schedule a mission from that stream? So let's take a look. So we can write a simple stream. In this case, we're just going to generate constantly passing in a string with the word next in it, and we're going to just run that pretty much constantly. But the second operation in our map operation, we're always going to throw a runtime exception, and then finally, if we get this far, we're going to print out the current value to the console. So what's going to happen here? Is our stream going to run constantly throwing runtime exceptions, or is it just going to simply blow up the first time and go into our ePrint stack trace? When we run it, kaboom, our application runs, but then it fails and the stream in its entirety is blown up. A single exception is enough to stop the execution of our stream. Now if we're trying to run this stream in some sort of schedule loop, one failure is going to be enough to end that loop, and if this loop is the main core of your application, it's going to just end your application as well. So in order to solve for this problem, we also need error handling. We've added in scheduling around our stream that has our core algorithm, but now we also need to wrap our stream execution in some form of error handling. And again, within your static stream utils extension methods class, you can add in, say, for example, a recover method, and that's exactly what we've done. So in recover, we take in the stream that may fail, and then we add in some sort of exception handling. In this case, we pass exception into a function, and we're just returning the value false, a boolean value, but it could be any value that you want to use to pass on to the next stage in your streams. But this is starting to get pretty gnarly. I mean, it's difficult to see even that when we have our lambda expression accepts the exception and returns false, where is that false being returned to? What exactly does that mean? It gets pretty gnarly whenever you begin to wrap streams inside streams using static methods, and we've lost the nice aesthetic of the typical stream data flow. So there must be a better alternative than this. This is perfectly fine to wrap a stream maybe at 1 or 2 levels, but once you begin to do anything of moderate complexity beyond what the stream API allows you to do, really you want something that gives you a more detailed stream-like flow. So an alternative to creating static extension methods is to create a static extension class, or sorry, just an extension class. So we can take our example application where we have our stream util schedule fixed delay and stream utils recover, and we could create an extended class that has these operators directly on them. So first port of call, if we're going to create an extended stream type, is it should have all the operators that a stream has, and it should be directly transferable with stream code. So what we've done is we've created this type reactive-seek, which is a sequential stream type with additional concepts for handling things like asynchronous execution, errors, windowing, and so on. And it extends to Java 8 stream, and it has all the same operators in Java 8, as Java 8 streams, so you can directly substitute it into your code where you're using a sequential Java 8 stream. And then on this type, we can add in directly a recover and schedule fixed delay operators, and we get back to the nice aesthetic of the typical stream data flow. And then in such a way, it's possible to leverage in a sequence much more complex operators and advanced operators that are provided on the JDK stream itself. And let's take an exact look at how that would work in practice. So we can create a stream. Again, we're going to iterate over the integers. In our map operation, for every third value, we're going to throw a runtime exception. Otherwise, we're going to return success plus the index. Within our recover section, we're going to return failed, and we're going to call e.getMessage on the exception. And if you notice, when we throw our runtime exception, we're passing the index in there. So essentially, within recover, we're going to have failed plus index. In our peak section, we're going to print out the current value, which will either be success index or failed index. And we're going to schedule a mission from this stream every second. So let's run this and see what happens. What we expect to see is, every third value should be failed with the current index, and every 2/3 of the value should be success with the current index. So you get failed 0, success 1, success 2, failed 3, success 4, and so on. So a reactive seek type builds upon a type called seek from a library, JLambda, which in turn extends Java 8 stream. JLambda is created by Lucas Eder, who also creates the Jug persistent framework. And this is a recent poll that he posted up on Twitter, where he's asking stream users how they use them. And very few people make use of the parallel feature within streams. So this is the insight that Lucas had, that the stream API was kept pretty neat and concise, primarily to support parallel streams execution, but in practice many developers don't use them. So by abandoning the parallelism inherent in the stream APIs, it's possible to build a much more powerful but purely sequential stream API instead. It might seem very odd that in a talk about building concurrent and parallel applications that we're talking about ditching data parallelism in favor of sequential operations, but this is a contradiction that will resolve later throughout this talk. Suffice to say that by ditching data parallelism, it's possible to build very powerful sequential stream types. And seek out of JLambda is explicitly short for sequential. In other languages like Scala, I think it may stand for sequence. In JLambda, it's explicitly sequential. So by extending the JDK stream but overriding and removing the parallel execution functionality that was present therein, it's possible to build an API that can do things like create sliding windows, zip streams together, which is a way of merging two different streams, duplication. And because Lucas comes from a background of building a persistent framework, there's a lot of very advanced and very nice SQL style operations added to JLambda Seek as well. And this is a great starting point for us. We want to encourage our engineers to write more code in a stream like data flow style, so a more powerful stream API is a really great start. But as we've seen, when we're building this microservice where we want to go off to S3 and transform the data, there's a lot of additional functionality and features that we'd like to have as well. Things like error handling. So within our reactive seek type, which extends JLambda seek and has all of the additional operators that have been added there, we've added in things for error handling and recovery. So we have the recover operator, for example, but there's also retry, which allows exponential backoff or various backoff strategies when we call unreliable methods, so that we don't just try once but we can retry it. If we're going to build parallel applications, support for asynchronous execution of our streams would be very useful as well. In the JDK, we have a concept of terminal operations, which are the final operations that trigger the execution of a lazily defined stream. In Cyclops-react, with our extended stream type, we are introducing the concept of a future operation, which essentially is a terminal operation that's executed on a future asynchronously. So all that happens when you call future operations, you pass in a standard Java executor, and then you get the same list of terminal operations that it's available on reactive-seek itself, which is an extended set including all of the terminal operations from JLambda Seek and from the JDK stream, and those get executed asynchronously on a separate thread managed by a completable future. So you get asynchronous execution of your streams. As we've seen previously, scheduling is also pretty useful as well. whenever you want to program in this stream-like way and do more advanced stuff this way. So not only can you schedule on a fixed delay, for example, or a fixed rate, you can also schedule using cron expressions so that when the cron expression is triggered, another data point will be emitted from your stream. Scheduled emissions from the stream in itself also produces another stream of data, and then it's possible to connect streams to that and then perform various operations on the output stream as well. So another useful feature to have in streams is the concept of a subscription or an event. To be able to subscribe to a stream and then control the emission of events from it allows you, for example, to apply back pressure across streams. So within the reactive seek type, you can take a subscription to it and then control how data gets emitted from it. And you can subscribe to various events within it, so you can capture on next events and error events and completion events as well. And all of this is possible really by implementing the reactive-streams API. So not only does implementing this API provide very additional useful functionality, one of the big benefits of it is interoperation across various implementations of this API. So what the reactive-streams API really does is, as its core, is provide a way for data providers and data consumers to interact. So streams are both potentially data providers and data consumers, and so are most of the data structures that we use. In Cyclops-react, nearly all of our data types implement reactive streams, and because of that, you get this really nice interoperability with libraries such as Pivotal's Reactor and RxJava2. And in the example here, you can see us generating a reactive seek from a Pivotal Reactor Flux. But it's also true with the extended collection types, which we'll mention briefly in a moment, that are part of Cyclops-react, that you can create an extended collection type directly from a Pivotal Reactor Flux and vice versa. Very simple interoperation because of the fact that both libraries implement the reactive-streams API. So by ditching data parallelism, it's possible to build a very rich streaming API. I won't go through all of the operators that we've added to reactive-seek in detail, but there's a huge number covering a wide range of different functionality types that are available. And most of this is possible because, like Julanda, we have abandoned the data parallelism in the standard JDK 8 stream. But we want to build parallel applications. But it turns out there are many ways that we could implement parallelism, and what we've done is take our extended stream type and layer parallelism back in, but just do it in a different way. And we've introduced the concept of future streams, which we'll cover later on, in order to do this. So within Cyclops-react, you have a concept of a future stream called lazy future stream that extends reactive-seek, so it gets all of these additional operators that reactive-seek has, but you get parallelism for free with them. And we do this by merging the concept of a stream, a JDK stream, and a future, something like a completable future. And so we want to encourage our engineers to program more in this kind of immutable stateless style that the stream API and optional completable future promote. And we do this by creating extended stream types, and we've created 2 extended stream types. But there's more than just the stream API in the JDK. We've got optional completable future, and it would be good to get extensions for those. Even common APIs across the methods and completable future, where the naming is different, would be useful. The same concepts can be applied to things like collections as well. In the JDK, currently you have to call, stream, perform some operations, and then collect back into the collection that you're using. And this is something that I think we can simplify as well, and that's what we've done in our library, is that not only have we created extended stream types, but there's extended types for APIs right across the JDK, and even for functional style controls structures that aren't present in the JDK but that you may be familiar with from other languages such as Scala. Right, so what I'd like to do now is cover how to leverage the 2 extended stream types to build concurrent applications. And in order to do that, I think it would be useful to establish a way or a model of visualizing streams. So we can take a pretty standard and straightforward sequential JDK stream example. So in this example, we have a stream of 4 values, 6512. We're going to perform a transformation operation defined by the map operator, where we're going to take each element and multiply it by 100. Then we'll filter out those which are over 551 and print out any that survive to the console. One way to visualize that would be as a simple sequential stream with 3 stages. First stage is our map operation, second stage filter, and final stage are for each. As data moves through the pipeline, 6 gets multiplied by 100, it becomes 600. We go to our filter stage, it's over 551, so it gets dropped. 5 becomes 500. It passes the filter stage being less than 551, and we'll write it out to the console. 2 will become 200, it will pass, and we'll write it out, and 1 will become 100, and so on. And that's maybe a way to visualize a standard Java sequential stream. Now we can turn our sequential stream into a parallel stream simply by using the parallel operator and using the visualization that we've defined for a sequential stream. What would that look like? It would look something like this. We split up the data before it gets pushed into the different rails of the parallel execution of the stream. So we have this kind of divide and conquer where we're splitting the data into each time, and then eventually it will get pushed through different rails of a pipeline in parallel. So that's one way to do parallel streams, but there are many ways to skin a cat. So let's look at a couple of alternatives. So if we have some CPU bound operations, one good technique, or one very simple technique to get efficient execution or parallel execution of streams is not to try and have the streams distribute the work themselves, but rather for us to take our standard sequential streams and distribute those. It's very simple, but don't knock simple. Simple can be good when you're building these types of applications. So a way to visualize that is that we have sequential streams but parallel pipelines. This is pretty good for CPU bound tasks where we've got the data that we need to process in memory, and we can distribute those across cores really on a thread per core model. If we want to implement something like this, it would help if our extended sequential stream made it easy to distribute the stream across cores. And we could do that by adding an operator that allowed us to target a particular thread. That is our future operations operator in the reactive-seek type. So let's take a look at some code. So we can take the stream code that we had before with the value 6512, and then we can use the future operations operator to have that stream target a particular thread. And this is one way of implementing that parallel execution of sequential streams. We can take a look at some code. So we define a for loop. We just create 4 streams and distribute them across threads. We can define a reactive-seek with our pretty standard stream definition. And each time we create the stream, we'll target a new thread. In our for each section, we'll print out both the current element and the thread on which we're executing. And when we run that, kaboom, we can see that our stream execution is distributed across a number of different threads in our system, 4 different threads. So this is pretty efficient for CPU bound operations. This thread per core model works quite well for when you have data in memory already. When you need to look up data from some form of external store, it's orders of magnitude slower to retrieve it from something like a hard drive or Amazon's S3 compared with the CPU's local cache or even RAM. And what will happen is if you try to do a thread per core model then is that your CPU sits around waiting idly for the data to come in from a remote source. So that's why when we compare the reactive-seek model of distributing sequential streams on a thread per core model, it's pretty efficient. Future streams, when I come to the details of how those work, conversely they're pretty good for IO bound operations, but the value that they add in being able to process data synchronously involves an overhead that makes them much less efficient at doing CPU bound tasks, so they're not recommended for that. If you want to do a lot of heavy CPU bound processing in a stream, a sequential stream distributed across cores is much simpler and faster. Okay, so let's take a look at how to solve the challenge of reading in large amounts of data or writing large amounts of data out in implementing an I/O bound algorithm using streams. So an alternative to taking sequential streams and distributing those across cores or threads, and also an alternative to taking data and splitting it up before you distribute it across reels of parallel stream execution, is to have a single pipeline and have it manage asynchronous tasks such as futures or completable futures. The completable futures and futures are pretty good for managing asynchronous blocking I/O operations. You can put the task up onto a separate thread. The current thread can continue to process. When data comes in to that future task, it can take over the CPU, and when it's waiting, another thread can execute on the CPU instead. So this turns out to be much more efficient for I/O bound operations. You can see there's some level of overhead here though, because our stream is now beginning to manage these future tasks, and this is maybe one way that might help you visualize what is going on whenever we merge together the concept of a stream and futures. So we essentially have the stream managing multiple futures, controlling how many futures are active, what those futures are doing, and so on. So let's delve into a little bit about what a future is in Java. So with the completable future API, it has a similar data flow declarative style of programming, and we can almost implement the streaming algorithm that we had previously. One core difference here though is that a completable future really only processes one value. It's not for a sequence of values, it's a single value passing through. So in the supply async, we're just going to load some data from somewhere via I/O. It's really there to highlight that these are pretty useful for I/O bound operations. The then apply method is it's the completable futures equivalent of map. It's exactly the same as a map operation in the stream API, and here we're multiplying the current number passing through by 100. There is no filter in completable future, so we can't do our filtering in a filter operation. Then except is like an asynchronous version of for each. It won't block, but whenever the previous stage is finished, maybe it's something maybe more like peak or for each. When the previous stage is finished, the value will get passed into then except. We can do our filtering there. We can't have an explicit filter elsewhere, so we can check if it's less than 551 before I put into the console. It's maybe not as pretty as the stream version, but we are able to implement something approaching the same algorithm as is possible with streams. Essentially this because both stream and completable future, even though there's no common interface, are implementing the same pattern. Now it would be nice if there was a common interface, and even if we had a common set of method names. So what we've done in Cyclops-react is create a future W or future wrapper. It essentially wraps completable future, but implements a more standard and common set of interfaces that we implement right throughout Cyclops-react, and uses more standard method names such as map and peak and filter. Now we've added a filter in here. Filtering on a future is quite difficult to do, so what we're actually returning from the filter method here is something equivalent to an optional. So this one looks much closer to the stream version. If you ignore the off supplier part where we're doing our asynchronous loading, it's very similar. We've got our map, we've got our filter, we've got our peak, and it could be a for each instead. Again though, core difference between this and the stream is that only one value can pass through it at a time. In order to solve the problem, we want to pass lots of values and have them execute asynchronously. Streams manage large sequences of values, potentially infinite sequence of values, and futures are pretty good at managing asynchronous execution. Put them both together and we've got a solution for large-scale asynchronous execution. So you can write this yourself. You can create a stream of completable futures. Things will get pretty gnarly very quickly though. So with inside our stream, what we need to do is create our completable future that does our asynchronous operation, and then within equivalent operations within the stream, for example within our map operation, we want to call the then apply operator on the completable future that's passing through. Filter's pretty difficult to implement. There's a lot of additional logic you'd have to put in for yourself, but you can get the concept here. And so on. Within peak we'll call then accept, and at the end when our our stream is completed, we try and extract the results out of our completable future in some way. You can do this. It's worth doing just to see how this would work. But I guess you probably don't want to be programming with these types of nested data structures all the time. It's pretty difficult to debug and maintain, and in terms of clarity, it's difficult to see exactly what's going on. Future W makes things maybe a little bit neater. You can see the analog of the stream operation in the nested operation on the future. So for example, we're calling stream map, we're calling future.map and so on. But still, dealing with these nested data structures is pretty gnarly. So that's why we've created a future stream. So what it does is it gives you a bog standard stream API, pretty much identical to any kind of the JDK stream, the reactive-seek type that we've created as well. You're not dealing with nested data structures. We deal with that for you in under the hood, and that's what's happening. So we create our stream as we would any other, but the fact we use the lazy react, which is our builder for our future stream type, and then in under the hood we will manage the execution and delivery of all the various future tasks. And if we want to see what that looks like in some code, we can create a future stream. In this case, we're giving it 4 threads to execute on, the same 4 values that we have before. We're going to do an asynchronous IO operation in there. When we get a result back, we'll multiply it by 100. We'll filter out those less than 551. And then in our peak operator, this time we will also output the element and the thread that it's been executed on. What run on current does, we can run the future stream and we could run it on another thread, or we can just run it asynchronously full stop, but this is telling us to block the current thread so our application doesn't exit while the future stream executes in parallel. And so when we run it, executes pretty quickly, and we can see that the data is output with each data point being output on a different thread. One of our values, the 6, is going to be dropped, which is why we only have 3 coming through. It's going to be dropped because it was filtered out as 600 being greater than 551. So in terms of performance for IO bound tasks, it's almost the inverse of the performance for CPU bound tasks. Future stream is much more efficient for handling IO bound tasks than, for example, a reactive-seek or a JDK stream distributed on a pipeline per core model, for the aforementioned reason that the CPU would be sitting idle as it waits for data to come in from a remote source. With a future stream, when the CPU is sitting idle, the JDK will swap in a different future on a different thread to continue executing that's ready to do some work. But between the two approaches, we have a streaming mechanism that's pretty efficient for both CPU bound operations and IO bound operations also. So if we go back to our algorithm, we've got 2 IO bound tasks. We've got to read data in from a log store, massive amount of data, so it would be really useful if we could do this in parallel. And now we have a streaming solution that might help us out. When we build our indexes in memory, we've got a large number of cores here, a large amount of data. It would be really nice to do that in parallel. It's a CPU bound operation, and we have a scheme as well for doing large scales parallel streaming operations on tasks that are CPU bound as well, using the reactive-seek type. And then finally, when we want to write the data back out to the index or in parallel, that's an IO bound operation, and we have a stream type of future stream. Again, that's pretty efficient for use in that use case. So we can delve a little deeper into this design and expand it out now to see what it would look like. So we can plug in our future stream to do our parallel streaming of our data in from, for example, something like AWS S3 or a network storage device. One of the key tasks here really should be to shard the data, because when we go into our reactive-seek types executing in parallel, what we'd really like is for each of those to be able to operate without impacting state external to the stream. In other words, we don't want them to contend with each other and have to worry about synchronization and locking. So one of the tasks of the future stream should be to shard the data so that each reactive-seek type executing in parallel gets data that's unique to itself. Once they build that index of the data that they have in memory, they can push that out to another future stream that can write the data in parallel out to something like AWS S3 or a network storage device. So we need a way to connect these streams up, and what we're proposing here is to use a queue. So in Cyclops-react, we have introduced a nice and advanced asynchronous queue type, which we'll talk about in more detail now. Connecting streams. So queues, what we mean by queues here aren't quite the JDK interface queue, although our queue type essentially does wrap it and offer a lot of the same operators. Probably we shouldn't have named it queue. We have this namespace convention with the JDK now, but this is something slightly more advanced and more suitable for this kind of asynchronous operation and connection of different string types together. So for example, we can simply connect the producing stream with a consuming stream via a queue. This is a pretty straightforward operation, and you could use something like reactive streams to connect two streams that implemented reactive streams rather than a queue. But with queues, we can do much more advanced operations. For example, we can connect multiple producers to multiple consumers and vice versa. So let's delve into the details of that a little. So to create a queue, in Cyclops-react we use the queue factories class, and it has a number of static methods. In this case, we're just creating a standard Java JDK blocking queue using the bounded queue operator, and we're giving it a max size of 1000. So within queue factories, there's a number of different factory methods, or you can create various both blocking queues and wait-free queues. We allow any queue type to be wrapped in this asynchronous type, and we come bundled with the Agrona library as well, which offers a number of advanced wait-free queues too. So once we have our queue, we can create a stream from it just by calling the stream operator, and essentially this stream will run and execute once its terminal operation has been invoked until the queue is explicitly closed. If you try to call stream on a standard JDK stream, what it'll do is it'll just drain the queue, immediately run to completion, and you can't push any new data into the queue, and so on. With these asynchronous queues, the queues essentially stay open. You can push more data into it. Your stream will continue to process it until you call queue close, in which case the queue will disconnect, the stream will disconnect from the queue, and the queue is finished, and the stream is finished also. So if we want to write data to a queue so that another stream can use it from, we can use the queue offer method. So offer is it's analogous to the offer method in the JDK queue interface, which means that for a queue that is a blocking queue, if the queue is full at this point, we will block. If it's got space, the data will get pushed in. So in this example, we're using a lazy future stream to read data in parallel and then push data into the queue, which another stream or multiple other streams can read from. As soon as it's there, they can get it. So one challenge that you have when you're connecting queues together is if the producer produces data at a rate faster than the consumer can consume it, and then you're opening up the possibility of running out of memory. So within the queue type, this is a good place to implement your back pressure algorithms and expose resistance to this. So if you use a JDK blocking queue, it may not be suitable for all use cases, but for most typical use cases of Java developers, it's probably okay. What will happen then is that once the queue is full and the producer tries to add data to it, the queue, because it's full, will simply block the producer, and the producer will no longer be able to produce data and fill up the queue, and the risk of running out of memory is alleviated. If your application has requirements or much higher latency, low latency requirements than I think probably is typical for the 90th percentile of Java applications, you may not want to block the producer in that case, because the producer thread will sit idle until it's notified that it can write back in. It may be more efficient in that case for your use case that the producer continues to hog the CPU that it's on, and that it implements some sort of strategy to determine whether or not it can actually add data to the queue. And Cyclops-react comes with a number of pluggable strategies, so you can have the producer simply hog the CPU and check, can I add my data point in, and as soon as it can, it'll get added in, or you can have it back off, and so on. Again, and conversely, if the queue is empty, you can have the consumer sleep until data gets added to the queue, or you could have it spin and back off as well. So let's take a look at some code hooking up two streams via a queue. So first thing we can do is create the queue. In this case, we're creating a transfer queue, which is a JDK blocking queue, or backed by a JDK blocking queue with a max size of 4 elements. Here we're creating a lazy future stream type. It's an infinite stream we're generating using a supplier that's going to pass basically the string data to the next stage repeatedly, forever, basically. In the map operator, the second stage, we're going to modify the string just to simply say produced on and add the thread ID on which this operator is executing. Now we've got an executor service with essentially 4 threads, so it's going to be one of 4 threads. The next stage, we're going to print that out, so we're going to see which thread the data has been produced on, and then in the subsequent stage, we're going to push that data point into the transfer queue. With the run operator, the future stream is going to run asynchronously. It's not going to block the current thread. So in the current thread, that gives us some scope to set up a stream that reads from the transfer queue. So in this case, we're pretty much dropping the data as soon as it comes through. In the map operator, we're not using the type at all, the element E that's been read from the queue, but we're just going to change that to a string that says some information about the consumer. So we're saying consumed on, and then we're adding in the thread ID. The future operations operator in this case means that, and the use of it here means that this stream is going to execute asynchronously on another thread as well, and then we're going to print out information about the consumer. So when we run this, we're going to get information about the interaction between a multi-threaded set of producers and a single thread of a consumer reading data from this queue, where the queue is in between and acts as an intermediary between the producers and the consumers. So when we run, we can see that we get the output like produced on a number of different threads and then consumed on a similar thread. So in this manner, you can use a queue to pass data between data producers and data consumers. So what this allows us to do is to create a consistent stream-based architecture right throughout our applications. We can efficiently use streams for I/O operations and also for CPU-bound operations, and we can completely and utterly avoid low-level Java concurrency primitives. You can build highly concurrent applications using low-level Java concurrency primitives. It's just very stressful and very difficult to maintain these types of applications. However, if your team is comfortable in leveraging streams, an alternative is using techniques such as the future stream and the stream per core model for CPU-bound tasks, is that you can architect your application so that essentially you're using streams and stream-like data flows throughout your application. You're completely avoiding low-level Java concurrency primitives, and one of the big advantages then that you get from this, as well as this consistent programming style, is you get an application with no locks as well. So it will perform pretty efficiently for you. So to summarize, which is easier to parallelize? Imperative, typical Java 7 imperative code, or the new style of functional data flows introduced to the Stream API? Well, it's most likely for most developers, most teams, going to be the stream style data flows way of programming. That's what we have found. That's why we've created the Cyclops-react library, to encourage our engineers to program more in this new stream-based way of programming, primarily because we're avoiding mutable state, which is the source of so much complexity in our applications, particularly once we make them concurrent. So a good starting point, if you want to build more advanced streaming APIs and encourage your engineers to program more in this style, is to develop a set of static extension methods. This is probably the first port of call for most engineers that are heading down this path, and it's a really great first way to get started. However, there are limits. The more you nest your various static calls, the more complex and difficult to maintain your application becomes. So an alternative is simply to build a more powerful extended stream type. And what we have discovered, building on top of the work of Lucas Eder, who really had this insight in the first place, is that by ditching the data parallelism of the JDK Stream API, it's possible to build a much more powerful and richer sequential API. And that's what we've done with reactive-seek, which builds on top of GLambda's seek type. But having created this more powerful sequential stream type, it's possible to layer back in parallelism. And we've done this in a different fashion. We've created this concept of a future stream, which merges the concept of futures and completable futures introduced in Java 8 with the concept of a stream. So essentially, the stream is managing a lot of these different futures and their execution in parallel, and that allows you both a rich API and powerful parallelism, particularly suited for doing and managing large-scale I/O. Once you have these different schemes for processing data in parallel, leveraging streams, it's pretty useful if there's another scheme for passing data between them. And the reactive-streams API does provide one way of doing it, but a more flexible and powerful alternative that can be used also is this concept of an asynchronous data transferring queue. And that's something else that we've built into Cyclops-react and that we use extensively in our own applications. So I hope you've enjoyed this talk and found it useful and informative. If you have, I really recommend that you do check out our Cyclops-react IO website that has a lot more detail and links that you can follow in to find out more about this application. It's really, really simplified the development of these highly concurrent applications for us. And if you're building these types of applications using traditional imperative style Java, I would really encourage you to take a look at this approach because it has made our lives orders of magnitude simpler. Thank you very much.